Have you ever thought about how our star, the Sun, came about and what will happen next? You are here, and this is our local star, the Sun. Once upon a time, 4.57 billion years ago, our Sun did not look like the Sun we know it as today. It all began with a massive molecular cloud of dust. These interstellar clouds are made up of molecular dust and gas, mostly molecular hydrogen. Their size varies from a few million kilometers to 600 light years in diameter and can weigh around 6 million solar masses. That is, 6 million times the mass of our Sun today. From these clouds, protostars are formed by molecular clouds collapsing onto themselves through huge gravitational forces to form a dense core of mass. Gravitational forces are the forces acting between any two objects with mass, an example of this being a single hydrogen molecule being attracted to several hydrogen molecules grouped together as seen here. Intuitively, the force would act towards the heavier object, and it does so with a force equaling g mm over r squared, with a direction vector showing which direction the force acts. This is the basis of how interstellar clouds come together to form a protostar. Over the course of 1 million years, material comes together to form a disk swirling around the protostar as seen here. As more material falls into the center of this disk due to the inward pressure of the gravitational force, the gas in the center begins to heat up to the point where nuclear fusion begins in the core of what is now a main sequence star. Nuclear fusion is the process by which two small nuclei of atoms join together to form one large nucleus and generate energy through the mass loss in the reaction. In the case of the core of a main sequence star, these light nuclei are hydrogen nuclei, and the larger nucleus is that of a helium atom. The way this fusion occurs is by the protons of the hydrogen nuclei coming together due to the high amounts of pressure in the core of the Sun. This produces deuterium, a positron, and an electron neutrino. From here, the deuterium binds with another proton to form a helium-3 isotope and gamma radiation. Once two of these reactions occur, and you have two helium-3 isotopes, they bind together to give a more stable helium-4 atom and two protons, which allows the reaction to start again. This is what is called a pp1 or proton-proton-1 chain. From here, we also have two further possible chains, as seen here. The pp2, whereby helium-3 and helium-4 come together to form beryllium, which eventually gives two helium-4 atoms via a lithium isotope, or a pp3 chain, which rather than going via a lithium isotope, goes via a boron isotope. Since there is a mass deficit between 4 protons and helium, we can use Einstein's E equals mc squared to show that the Sun produces 3.86 times 10 to the 26 joules of energy per second. This means the Sun generates 6.8 times 10 to the 7 times the world's annual energy consumption every second. When nuclear fusion begins, our Sun enters the main sequence phase, whereby nuclear fusion generates energy to create an outward gas pressure, which is in hydrostatic equilibrium with the inward force of the gravitational pressure. Presently, our Sun, along with 90% of the stars in our universe, is in the main sequence stage of its evolution and is approximately halfway through its predicted lifespan of 9.5 billion years. Once all of the available hydrogen in the core has been depleted, fusion reactions begin to cease. When no more fusion occurs in the core of the Sun, it will become heavier and its core will contract due to its own gravity, making it a red giant. As you can see, red giants are vast. Once our Sun reaches this stage of its lifespan, its outer shells become dense enough for nuclear fusion to occur. This causes the outer layers to expand, which is what creates its enormous size. At this point, the surface temperature decreases and the Sun will appear red, hence its name a red giant. Once the outer layers have expanded far away enough from the Sun's core to escape the gravitational force, the outer layers float away to give a planetary nebula. At this point, the outer layers are the dust which forms up gas clouds, restarting the next generation of star formation. What is left over when the planetary nebula escapes is a core of burning materials, making a small but brightly dense sphere where no nuclear fusion is occurring, called a white dwarf. Since there is no outward pressure due to nuclear fusion, what opposes the gravitational force is electron degeneracy pressure. This white dwarf is so dense that one spoonful of its matter would weigh roughly 5 tons here on Earth. That's the same weight as a spoon with an elephant on it. Since there is no source of fuel, the white dwarf will gradually radiate its energy away and cool down, beginning to crystallize. This leaves behind a black dwarf. Since this process of cooling down is theorized to take longer than the age of our universe, we have not yet found a black dwarf. Even if there were black dwarfs, we could not directly detect them since they do not radiate. So here is a beautiful picture of our galaxy to finish off this video.